Greetings, participants, and welcome to this next session of the Africa Calls lecture series. I am so thrilled to introduce our next speaker, which is Dr. Liren Pantanowicz. Dr. Liren Pantanowicz is a professor in the Department of Pathology and the director of anatomic pathology at the University of Michigan in Ann Arbor, Michigan. He received his medical degree from the University of Witwatersrand in South Africa. He completed his anatomical and clinical pathology residency, as well as hematopathology fellowship training at the Beth Israel Deaconess Medical Center and Harvard Medical School in Boston, followed by cytopathology fellowship at Tufts, also in Boston. He is board certified by the American Board of Pathology in clinical informatics and also completed his master in health administration at Ohio University. Dr. Pantanowicz is an editor-in-chief of the Journal of Pathology Informatics. He is the president of the Digital Pathology Association, the president of the American Society of Cytopathology, and a past president and current council member of the Association of Pathology Informatics. He is widely published in the field of pathology informatics and cytopathology. His research interests include digital pathology and artificial intelligence, as well as non-gynecologic cytopathology. For longstanding audience members, they may recall Dr. Pantanowicz spoke in this lecture series 5 years ago and one day on the role of informatics in patient-centered care and personalized medicine. We are so pleased to have him back and really excited to hear him speak specifically about digital cytology and emerging AI applications. And so with that, I will turn that over to Dr. Pantanowicz.
Thank you, Leslie, and thank you to the organizers for the opportunity to present to everyone in Africa. I'm going to be talking about digital cytology and emerging artificial intelligence applications in that particular area. What I'd like to address is look at the current state of digital cytology. Why should we be adopting artificial intelligence if we practice in this area? And then it's obviously not that simple because not all of us are doing it, even here in the USA. So what are the barriers to artificial intelligence implementation? As most of you know, just like I do, because I'm a practicing pathologist in the area of cytopathology, there are many unmet needs that are exhausting. Our workload is forever increasing. The complexity of the cases is increasing, asking us to do many ancillary tests, molecular testing. There's fewer of us to do this work, less and less subspecialists to go around. Pathology is often marginalized. We're not often in the discussion, especially with the latest parts of precision medicine. And there are many advances coming our way that make us do many more complicated things that are sometimes difficult to do. PD-L1 is an example. To try and provide a score for people on a cell block is challenging. And, COVID came along, as all of us know, and the burnout that we have felt from that is pretty real. So something has to change for us to get back to a world where we used to practice in, and hopefully computers can provide that edge. I understand in Africa, not all of you may have the resources to implement digital cytology and get the latest instruments and software, but I'd like to present to you what is available and what we are working with, at least in the USA and other European countries, so that you are aware of what is available, and hopefully one day we'll make it to your lab. So I'd like to cover just a brief overview of artificial intelligence, keeping it simple, and then the PAP test has been automated for a while, and what can we learn from that to apply today? If we're going to do AI, we need some sort of digital cytology platform, and I'll talk to you a bit about that. And then how easy is it to make an algorithm in cytology? I'd like to explain that to you. Once you have AI, it's like a new microscope to discover the world, especially if you want to make discoveries in cytology. And I'll give you an example of how I use AI to do that. And then finally, we'll just talk about some practical things, trying to implement and put this into practice. So let's begin with an overview of artificial intelligence. Well, we have reached this era of what we call computational cytology, using computers to help practice in the field of pathology, because now we have digital cytology, we can digitize and scan slides. And once we have those digital images with all the pixels containing data, we can apply artificial intelligence. And the field of AI has advanced a lot too. People have gone from simple algorithms to very complicated algorithms, which sort of mimic the human brain artificially. So under the area of artificial intelligence, that umbrella contains two main groups of building algorithms. There's machine learning and deep learning. Machine learning, as you can see on the top panel, is when you take an image and you have a human extract certain features from that. And usually they annotate cells, NC ratio, and so on. And then based on that, you can classify the image. So when the algorithm sees an unknown image, it will know how to classify it and give you the output. It's usually supervised because you have a human, perhaps an expert pathologist, help put the data in so the computer algorithm can make a decision. Deep learning, on the other hand, which is more advanced, as the bottom panel shows, does not require a human usually to provide any input into the classification of the image. What you need are large numbers of images, a large digital data set. And when you feed those into your artificial brain, also known as a convolutional neural network, when you deal with pathology images, the algorithm will learn from itself how to make decisions on its own, the trends and based how the pixels are arranged and so forth in the image. And then it will give you the output desired. And many times all you have to do is use images and not humans. So it's a little bit quicker and cheaper in what we call unsupervised learning. Now, when the algorithm provides us with an output, usually that is interpreted best by data scientists and computer scientists because there's a lot of numbers, mathematics, statistics, and probabilities, which doesn't really help us as practicing pathologists and cytologists. What we need is something a little bit more easy in what we call explainable AI. So the data could be presented, as you can see on the left, as a heat map. So in this particular area of prostate cancer, or this particular area with prostate cancer, you can see that the algorithm identified those glands as being abnormal, high probability of being malignant. And so you put a heat map where red is the highest probability. And so as a pathologist, I can now see, oh, that's where it's localized and red means it's malignant. Alternatively, you can have the data presented to you as images or thumbnails. And usually what a lot of people do is present that to us as the end user in a gallery, as you can see on this cockpit shown on the right. So a lot of pictures will be ranked as which are the highest probability of showing an abnormality. And you can see pretty quickly that the output here is, oh, these are images of poilocytes due to HPV infection. And so this is a low-grade squamous intraepithelial lesion. And so that's, in a way, explaining the AI output to us as human end users. Now, a little note about the galleries is if you have an AI algorithm present the data to you in the form of a gallery, we looked at if this is a good idea or not a good idea, or should the data be presented in another way, especially when you're trying to review a cytology case. And it works very well, no matter what the cytology use case. It could be pap tests, could be screening urine cytology, effusions with malignant cells, and so forth. But what we did find is that if you have too many images in the gallery, it's confusing for humans. And so what we found is when we had cytopathologists look at galleries, one, the gallery size is too big. People just land up calling everything atypical, and they don't commit to a definitive diagnosis. And we found that the optimal number of images to show a human in a gallery is probably 24. And so if you show someone 24 images, like you can see on the right, this is a urine specimen, and there's a gallery of 24 images, you can quickly see that those are all atypical cells. This is probably a high-grade urothelial carcinoma. And so it's quick and easy to do it that way. Now let's look at the pap test and what we could learn from our experience in automating that. As many of you know, some, but not all labs around the world have used automation of their pap tests. That means the slides get prepared in a particular way. Those slides can then be imaged on devices, such as a thin prep or SurePath method, and it can be screened by a technologist, or if they're negative, reported directly out. And in some countries, such as the US, those have been FDA approved for this exact reason, to help screen pap tests. Now, CAD stands for computer-aided diagnosis. We now know, because this has been around for almost 2 decades, that computer-aided diagnosis to help with Pap tests has had positive outcomes. Number one, it has increased productivity. If you use computers to help you, it can be cost-effective, especially if you're a high-volume lab. If you have thousands and thousands of Paps, well, then you can certainly use assistance of a computer to screen that. And what we found that humans cannot screen as many cases as we would like, and therefore we had to adjust workload limits. Just because you can screen unlimited number of cases with the help of a computer doesn't mean you should. There's only so many cases one can look at before your brain explodes or you make a mistake. So we have changed workload limits accordingly. Well, does it really make a difference? And we now know over time that, yeah, computers are a little bit more sensitive than humans in Pap tests, especially for detecting the low-grade cases, but not as much for every other lesion, but they're certainly a little bit more sensitive. As you can see on the right, this is an example of one publication I pulled back in the day in 2008, where you can see this cytology lab, after 6 months of using their imager system, you can see how the productivity for their cytotests increased remarkably. But it is true that if you bring in new technology, you have to pay for it. And so every additional advancement in the screening of Pap test will drive the cost of the Pap test up. So what we learned is that people are afraid of bringing on AI today because regulatory bodies, like in the US, the FDA, or in Europe, CE mark approval, they may not give us approval to use AI, but that's not true. If you look at decades ago from Pap tests, yeah, all these regulatory bodies approved using computers to help us screen Pap tests. One thing that the vendors did, vendors like Hologic, for example, that provide these systems to screen Pap tests with computers, is they took care of the whole process. They didn't just take care of the imaging or the analysis part, they took care of all the pre-imaging part. So they told you what fixative to use, how to process, make a liquid-based slide, and what stains to use, and how to make a monolayer, because that makes a better image. I believe in the principle of GIGO, which is garbage in, garbage out. Today, in the world of artificial intelligence and digital pathology, not many of the vendors care what happens before the image, which is a problem. When this was first introduced, a lot of cytology labs complained this was too disruptive and they didn't want to do it. But over time, now many labs, at least in the Western world, are using automated screening. One of the things that we should take note of is that these computers were designed to automate Pap tests because they were solving a real problem. We needed automation. There were just not enough techs, and they helped improve accuracy. Today, many people are building AI algorithms where we don't really even have a problem, and so it's hard to justify using them. As mentioned in the slide before, there have been favorable outcomes. These automated screening systems have been a little more sensitive and productive compared to humans, especially for large volumes. And we have realized now that these automated systems are not going to pick up every rare lesion in a Pap test. So some rare atypical glandular cells may be due to a fallopian tube carcinoma or metastatic breast cancer. Yes, the algorithm may not pick those up, but it was never designed for that. And to be honest, a Pap test wasn't designed to screen for those kind of malignancies either anyway. But one of the main things that did drive the field was we could get paid if we build for the technical and professional component to use these computer systems. Today, with some of the new AI algorithms coming about, the justification for the business use case is not quite there because there aren't billing codes or reasons for insurance companies to pay for using AI. So let's look at digital cytology and what kind of platform do we need to get onto so we can have all these apps like we would want on a smartphone. Well, there are many labs, not that many, but there are many labs around the world in different countries that have gone fully digital. They've given up their microscopes and they are now doing what we call primary diagnosis. And this is mostly for surgical pathology. When it comes to cytopathology, not too many labs have gone fully digital. People scan slides for education and research, but to actually screen and sign out those cases, very few labs have started using digital scanners for digital cytology. Now, As mentioned, whole site imaging technologies is not as pervasive in cytology for two main reasons. One, it's hard to make a good image. The image acquisition has problems, mostly due to focusing. And two, the workflow in cytology is a little different. We usually screen, and we usually have more than one person screen a case, a cytologist and then a pathologist. The focus problems arise, as you probably know from following the literature and what's happening in the field, is our cytology material has thick three-dimensional clusters between the slide and the cover slip, and we can have obscuring material like blood covering those cells. And even liquid-based slides that have a nice monolayer can still have 3D cell clusters, those typical hyperchromatic crowded groups in PAPs. If you only scan them in one layer, you can't focus on everything that's going on. So we need to scan slides in multiple focal planes, and many of the companies that have provided scanners today, if you use their systems, will increase the scan time and the file size, which is not practical for everyday use. Screening a regular glass slide itself is tedious. Trying to do that digitally is even more time consuming and ergonomically difficult, especially if you're trying to use a computer mouse or use tools to click and annotate. So if this has to be useful for us in everyday routine practice, we need a dedicated system that's going to fix these problems, which is help us get a good image, everything is in focus, and it makes sense for us with the kind of workflow we have, which is screening cases before we interpret them. Here's an example of a digital image of a Pap test. This patient had melanoma of her vagina, and this image shows two things. One, in the background are lots of malignant individual melanoma cells, but there are also large clusters of malignant groups of cells, such as in the middle. Now, this slide was only scanned in one plane, sort of what we call one Z-axis. And so everything in that field, in that plane, will be in focus, which are the single cells, but everything that is out of focus will have been out of that scanned plane, such as those 3D clusters, and that is why you can't see that in focus. This is what happens when you scan with just one layer. There are new digital cytology systems that address that. An example is shown to the right from Hologic, their new Genius digital diagnostic system. Now, I have no conflict of interest with this company. I've not received any financial money from them to talk about this product, but I have used this product. There are some labs around the world that have started to deploy this, some in the USA, Germany, Europe, like the UK. There are a few labs that have started to use this system. Basically, when you scan your thin prep slide, that image goes onto a server, allows artificial intelligence algorithms to analyze that, and then the output is given to the end user on what's called a review station, computer monitor. The whole site imaging process is optimized for cytology, and that is because they use volumetric scanning, which is new and novel, and I'll explain that to you. And they then run artificial intelligence algorithms on that. So the output, as I explained, is given to you, the end user, the human, in a gallery, so it's easy to review. Currently, there's an algorithm for use with Pap tests, and hopefully more will follow for other non-gynecological applications, CSF, effusions, thyroid FNA, and so forth. This is what the scanner looks like. It's called a Genius scanner. Now, if you do decide to use the system, you have to use Hologic's imager stain. You can't just take any slide and put it on and have the algorithm run that. The scanner can use other slides to digitize, but if you want them to be analyzed by the algorithm, you need to use the Hologic imager stain. That is because you need good pre-imaging qualities before you can analyze the image. The scanner can hold 400 slides. Each carrier has 40 slides, and you can see in this picture that it has those 2 racks, so quite easy to load. And in our experience, it's about 1.5 gigabytes for a whole site image. So you could fill up, a server in a short time if you have thousands and thousands of PAPs to analyze. Now, the problem I'd mentioned is you need to be able to focus on your cytology material. And if you have 3-dimensional cell clusters, as shown in this image, and you want to focus up and down in what we call the Z-axis, you will need to scan in multiple layers, as shown on the right. And some scanners allow you to do what's called Z-stacking. You can set 1 or up to 1 to 11 layers and you can set the distance between them and then go ahead and scan the slide. But that takes much longer. In this case, it would take 11 times longer to scan the slide, and you have 11 times the file size, which is expensive to store. An alternative way of doing it is what's called volumetric scanning. So what you do is you can see on the left, if you scan your slide in multiple layers with a Z-stack, and then what you do is you only pick those patches, those image patches, which are in best focus. And then once you have just those patches that are in focus, you stitch those together in a final image at the end. And so you just have a single flat file, which is much smaller, and this takes much quicker because you can scan all of those layers in at the same time. And that's what the Genius system has done. So it will scan ThinPrep PAP slides in at 14 different focal planes, separated by about 2 microns between each layer. And then it merges all those single focal layers and where each pixel is optimally focused. And so at the end, like this group of adenocarcinoma cells in a PAP test, you can see this 3-dimensional cluster is now well visualized, and the cellular detail is clear in the image on the right in every single cell. You don't have to focus up and down because the image now captures that for you. And then after you apply artificial intelligence algorithms to analyze the entire PAP test, which could have up to 100,000 or 200,000 cells, the data is presented to you in this sort of format on a computer monitor, which is a digital cockpit. And so on the left, you have the image gallery, which is the explainable AI. And so now you have the AI showing you the most highly ranked abnormal image patches, which hopefully have the abnormal cells. On the top would be the low-grade cells, the second row high-grade cells, glandular cells, bugs, and so on. And then a human can still review that. And then on the right is the whole slide image, which is the cell spot. That's the circle of the ThinPrep. And you can go ahead and navigate any particular area. So you can see on the image on the left in the top row, we've clicked on one group of low-grade cells, which takes you to the exact sort of GPS location on the cell spot. And then you can go and navigate and see if it makes sense and look at the milieu in the background and see if you've missed trick and so forth. And a lot of users tend to like this sort of presentation. And we wanted to see what users actually thought about doing this. So I was involved in a study together with Dr. Sarah Harrington from Hologic. And what we did was create this educational website, which every week presents new PAP test cases. If you're interested, I've given you the link. There's the URL to log on to this educational website, which is free. Just over a year time frame, we had over 51,000 cases reviewed by almost 900 people. And at the end of the day, what we found was most people like this. They found this quick and easy to use, which suggests that they're willing to give up the microscope at least to screen PAP tests. And so this was favorably received by a global community. Now, at the University of Michigan, Michigan Medicine, we asked Hologic to give us one of these systems so we can validate it for clinical use. On the left is how we did our validation study. I will be honest with you, we had no guidelines because there are no published guidelines out there that I'm aware of that tell cytology labs how to validate AI systems. So what we did was when we received a PAP test and we made a ThinPrep slide, on the left arm of the validation, we signed it out the usual way, which is we gave it to a cytotechnologist and a pathologist, and they reviewed it. If it needed HPV testing, that was done. And then they signed out an official report. And we used that arm as our ground truth. And then on the right, we did a new stain to make sure it was compatible with the imager. We had another human review it again in the clinical trial or the validation, and then we put it on the scanner, we scanned it, and on the workstation, we had humans make a digital diagnosis. And so we could compare the digital diagnosis with AI support to a manual diagnosis and the official report. And what we found is on the right, you can see the results are that doing this digitally with AI support is not inferior to doing it manually. In other words, it's just the same. So you can give up your microscope to do it digitally. In fact, what we found, and the data will be published soon, is that doing it digitally with the help of AI, we actually saw some increased accuracy, especially in the atypical categories. It definitely improved our workflow. You can see doing it digitally took us half the amount of time to screen a pap test compared to doing it manually. In fact, I'll be honest with you, some of the pap test slides, especially the low-grade cases, took me a couple of seconds to make a diagnosis. Because once I looked at the case and I saw those quoticytes and I knew this is a low-grade case and I couldn't see anything else, no bugs, no high-grade case, no high-grade cells, and I trusted the AI, I was happy to make a diagnosis within seconds. And when we asked people how they felt, which included 6 cytotechnologists and 3 pathologists who did this validation study, all of them subjectively said that they liked this and would use it every day. Plus, they no longer are tethered to their microscope. So now they could work anywhere. They don't have to be, stuck to a desk in an office at a microscope. They could be rotating anywhere or even work from home if necessary. Now, Hologic are not the only company out there that provide AI-based pap test systems. Here's an example of another 3, or here's examples of another 3. On the left, OptraScan provide a system. Datexum from France provide a similar system, and TechSite also provide a system. Again, I have no conflict of interest with any of these companies, but I just want you to be aware that there are at least now 4 solutions out there commercially available that are being marketed for analyzing pap tests digitally with the help of artificial intelligence. So how easy or difficult is it to make an algorithm in the field of cytopathology? Let's look at that. A few years ago, I reviewed the entire literature to see, well, who was working on artificial intelligence in the field of cytopathology and what were they doing? And we published that in the Journal of the ASC. And basically what I found is that there are lots of people around the world, especially computer scientists, working on pap tests, mostly the squamous lesions, some on urine cytology, a few on pleural effusions, and then it tapered out a little bit, less on thyroid, some on bile duct, very few on pancreas, and some on breast FNA. And as you probably know, these can be challenging areas to provide a definitive diagnosis and not just stick a case into atypical or suspicious. So we certainly could use the help of artificial intelligence to refine our interpretations. Well, there are problems when it comes to building a deep learning algorithm that everyone experiences in pathology, not just in the field of cytopathology. Number one is we don't have these large digital data sets available. Many labs have not been fully digital and don't have slides scanned. So if they want to work with AI, they have to first scan their slides. And it takes a long time to generate these data sets because you have to label all the slides. And if you want a supervised algorithm, you may even have to annotate that. It becomes expensive for all this computer technology, and especially humans who understand and can use this technology. The algorithms are very context specific. And what I mean by that is if you build an algorithm to do one thing, that's all it will do. So if you build an algorithm to detect squamous lesions, that's all it will do. It's not going to find bugs like herpes on a pap test. It's not going to find glandular lesions and so on. You have to build multiple algorithms. Some of the complaints people have now is algorithms are biased, especially if you build them on sort of say in the USA, just on one group of patients. Will that be applicable to patients in Africa? I don't know. How do we evaluate the performance of these algorithms? And will they be generalizable? In other words, if an algorithm is built by a research company in partnership with one lab, can they generalize it and plug it into your lab? And will it work on your cases, on your images, with your stains, and so on? So we do not have enough experience yet. Many people complain about AI being a black box. So if it goes wrong, we don't know what went wrong. How do we even troubleshoot if that's the case? And they lack a lot of flexibility, these algorithms. Once you build them, it's not that easy to go in and change things. It requires a lot of computer programming to do that. We're also not quite sure about how regulations should oversee algorithms. Can they just sign up cases on their own? Do humans have to oversee this process? And as mentioned, how do you validate this? I gave you an example of what we did in our lab here in the USA, in Ann Arbor, Michigan, but there aren't standard guidelines out there on what we should all do. I think we do need a recipe so we can all follow so that we're at least practicing safely. Now, it's very hard to get examples of all the cases you need to build an algorithm, especially if you want an unsupervised algorithm with deep learning. You may need thousands and thousands of cases, and who has thousands and thousands of rare cases? So here's an interesting paper that my colleagues in South Africa, in Johannesburg, developed. Was they made synthetic images. So what they did was they created synthetic images, and in this paper they published in the Journal of ASC, they made synthetic malignant urine cytology images, and they successfully did that. And once they did that, they could now boost the training of algorithms and get enough cases to build AI. At the same time, you can use that for training and so forth. But it becomes even harder to build an AI algorithm due to some nuances in the field of cytology itself. And here are some points that you should be aware of. Even if you have AI, almost all labs do not have a digital workflow. And you really can't do AI unless you do digital first. You can't build AI, and you can't even deploy AI. Next is, it's not quite clear how these algorithms should be used. What algorithms do we really want? Do we just need help with screening, or do we actually need help to screen and interpret so we can make a diagnosis on a case? In other words, if it were urine, do we just want to know that this is benign or malignant, or do we want it to go further than that, that this is a low-grade versus a high-grade urothelial carcinoma? Do we train algorithms just to replicate the existing classification systems we have, which is what most people are doing now? So for Pap tests, we pigeonhole the cases into the Bethesda system. Maybe for urine, we pigeonhole it into the Paris system. And there are many systems coming out now, Milan and other systems. But why are we training algorithms to systems that humans have arbitrarily designed? Perhaps we should train the algorithms to outcomes. Well, how do these patients behave, and how do they respond to therapy? Maybe that's a better way to train algorithms, but we're not doing that yet. We also have many cytology preparations. And even though there are different slides, they still have the same data. So you could have a liquid-based slide, you could have a conventional smear, and you can't train AI on liquid-based, but then have it run on a smear. Won't work well. As mentioned earlier, we have a lot of problems digitizing our cytology slides. They may not always be in focus. The three-dimensional cell groups especially may be out of focus. And so if the resolution is poor, you can't analyze that data. The cytology material itself is tricky. Cells could be overlapping or obscured by material. And when that's the case, it's hard for a computer algorithm to sort of segment those out. Say, I'll analyze this cell, and then I'll analyze the next cell. If they're overlapping and obscured, it's hard for the computer algorithm just to sort of segment and say, let's focus on this cell and then analyze those features. We probably need multiple algorithms just for one use case, like adequacy and then all the diagnoses. So for the Pap test, we need to, number one, determine if the Pap is adequate. And then once it's adequate, then look for squamous lesions, glandular lesions, bugs, or whatever else we want. So multiple algorithms have to run simultaneously. And as I mentioned, our workflow is a little unique. We need a system that incorporates both the screener, which is our cytotechnologist, and the cytopathologist who will review the case afterwards. So those are all unique problems. Here's an example just to show you. Let's say we decided to build an algorithm for thyroid FNAs. In the case of papillary thyroid carcinoma, if we have an algorithm to detect papillary thyroid carcinoma, how do you design the algorithm? Do you do it with a diff-quick smear or a Pap stain slide or liquid-based or a cell block? Because you can see on the right, although you would probably agree with me that all those images nicely show papillary thyroid carcinoma, beautiful intranuclear inclusions, etc. The presentation is very different, and so you'd have to train 4 different algorithms based on these preparations. I also wanted to show you some examples of, when you ask a computer algorithm to analyze cells in cytology material, there are a lot of artifacts that have to be overcome. And here are just 3 examples. So on the left, those are urothelial cells in urine cytology, and it's out of focus. It wasn't scanned. It was in volumetric scanning. So that's just a one-plane scan, and you can see that's out of focus. So it's hard for the algorithm to actually determine what that detail is. On the right, you can see these are 2 urothelial cells that are overlapping. And again, that may be challenging for the computer algorithm to decide, is this 1 or 2 cells, or is that a cell in cell? It's difficult. And then on the third image on the right, you can see that there's some artificial stitching of the image, and you can see where two different areas of the image were stitched together. There's a line that goes through the image, and that's an artifact. But if you're asking an algorithm to analyze sort of nuclear irregularity, if those artifacts go through the nucleus and the nuclear membrane becomes artificially irregular, the irregularity will be counted as being abnormal in that cell. So all of these things can cause false interpretations when using AI. So let's look at another use case other than the Pap test. And a good use case is urine cytology. This is a great match for AI. These are high volume specimens. They can be easily processed with liquid-based cytology, and the workflow is exactly like Pap test screening. The problem is with urine, there's a high atypical rate, which patients don't like because it causes them anxiety, and it increases the cost for healthcare in general. If you keep signing out a urine as atypical, these patients have to come back and get re-examined, maybe even have cystoscopy done, which drives up the cost of healthcare in general. And the literature has shown that we as a cytology community do not do a very good job at screening urines. We have poor inter-observer agreement. What one person may call suspicious, the other person may not. At least we have a parasystem for reporting this out now, which is quite standardized and being adopted by many cytology labs. So if you wanted to build AI for this use case, you could just use the parasystem as a structure to do that. For those of you who use the parasystem, you'll know that the approach to urine diagnosis is pretty helpful. But I'll point out two things: that while many of the criteria we use in the parasystem are qualitative, like hyperchromasia, coarse chromatin, and so on, the parasystem does use quantitative criteria, like the NC ratio. They have cutoffs of 0.5, as you can see in the boxes, 0.5 and 0.7. And as a human, I'm not sure if I can tell the difference between 0.5 and 0.7 that well. And even counting abnormal cells, you can see on the bottom right is when you have atypical cells. The parasystem says if you have sort of between 5 and 10 and they're rare, maybe just put that in suspicious, but don't call it positive yet. I'm not sure if I'm counting all the right cells to put the case in the right category. So these quantitative criteria make it difficult for humans to be very precise. And this is the exact premise of this paper that Dr. Layfield and colleagues published back in 2017. They took 47 cells from Pap stained urine cases, and they looked at the NC ratio, which is an important criteria for the parasystem. And they had this done by quantitative image analysis. That's what QIA is. And they had humans, 6 pathologists, look at the NC ratio. And to be honest, the accuracy was not very good. Only about half the cases, 53% of the cases, did humans get it right for that 0.4, 0.8 NC ratio, as you can see on the graph at the bottom, that the higher the NC ratio, we're all over the map. We get worse and worse the higher the NC ratio is. And the kappa is only 0.5. So basically, it's the flip of a coin if you want to call something high grade or not. In other words, what Dr. Layfield said is that visual quantification, if we were asking humans to do this, we cannot really categorize cases very well, especially as the NC ratio gets higher. So there must be a better way to do this. And Leopold Koss, even back in the 1980s, realized that computers are probably the way to do this and to help automate the whole process. Let's automate this and use image analysis, which is exactly what Dr. Koss started to do back in the day when he was a prominent researcher. He built his own image analysis system, and he employed 3 phases back then. He digitized the urine sediments, and he extracted certain features from morphometry, and then he classified the urine cells. And basically, he was able to make a diagnosis, even back in the 1980s, which is the birth of, computer-assisted screening in cytology. Since then, there have been papers where people have applied modern technology, like deep learning. Here are 2 examples where people have been able to use AI to automate the parasystem. And both of these papers report excellent results. I was involved in a project where we did the same thing, which we published back in 2019. So we built an AI algorithm, again, to report urine cytology. We took 2,400 thin prep slides from both voided and instrumented samples, and we created this deep learning algorithm based on the whole slide images. And we used almost 2 million urothelial cells to train the algorithm. And we didn't just look at the individual cell features like NC ratio. We also looked at the whole slide features. These are things that we don't usually count and attribute to being abnormal. like the way cells are distributed on a slide and how many cells are distributed on a slide, and adhesion, especially when it comes to urine. But the algorithm figured that those are important things that are worth using to help make an interpretation. And you can see the AUC, the area under the curve, is 0.88, which is pretty good. It's not 1. 1 would be perfect, but 0.88 is better than many cytopathologists today who pigeonhole many of their cases as atypical and suspicious. And here's the computational pipeline just to show you what we did. So on the top, we took cell level features. Those are the typical ones that the parasystem uses, NC ratio, hyperchromasia, nuclear irregularity. But there were also slide level features, such as just the degree of cellularity. The orange dots are all the malignant cells. And you can see in a high grade case, there are many of them spread all over the slide, which is typical. And based on all of those features, the algorithm could pigeonhole a case according to the parasystem. I will tell you that there were more than like 120 features the algorithm used, and many of them are not human readable. They were just statistical computer numbers that the algorithm had learned from the images, but I, as a pathologist, could not understand what the algorithm was interpreting, but yet it got it correct. Now, what I find most exciting is, can AI be developed to do something more than I can at my microscope? Yeah, so what? I can screen a case, so can the algorithm. I can interpret it as high grade or not, so can the algorithm. But what I cannot do is predict, well, if I'm looking at a high grade case, is this actually going to be invasive when you look at a biopsy or not? It's hard to determine that. But here's an example of a paper that was published not so long ago, where these investigators did show that you can do much more with AI than humans can do. And I think that's really the key, and maybe one of the biggest drivers for us to use artificial intelligence is it will be able to do things that we cannot. What we can do pretty well now is maybe a diagnosis, but what AI algorithms will maybe do better is actually make a prognosis and make some predictions that we struggle to do on morphology alone today. So let's look at making new discoveries with the use of artificial intelligence. A few years ago, this popular magazine known as The Pathologist interviewed me. And one of the things they asked me is, what do I like about artificial intelligence? And what I said I like a lot is that, I can now use AI to do my discoveries. I am an academic pathologist and I like to do research and discover things. And I always find questions that we need to answer. And I used to answer many of those with a microscope. I'd look at cases through my microscope and try and discover, new trends, new associations, new morphological findings. But I have found that using AI, I can do that much better than I can with a microscope. So let me give you an example. For those of you who do look at urine cytology cases, you probably have encountered this phenomenon, which some people call cannibalism, or what we can also call a cell-in-cell arrangement. Now, there have been very few papers about this in the literature. Here's one paper back from 1998 from these Japanese researchers where they found cannibalism, but only in like 300 positive cases. And usually it was associated with a high-grade, muscle-invasive, progressing urothelial carcinoma. Whenever I see a urine cytology case that has a cell-in-cell arrangement, it's almost pathognomonic of high-grade urothelial carcinoma, but this is not in any textbooks. There are only 2 publications, as I mentioned. This feature has not even made it into the parasystem. So I wondered if this was true or not. And usually when I teach people that are training with me, I usually tell them that if you see a cell-in-cell arrangement in a urine cytology case, you can probably be rest assured you're dealing with a high-grade urothelial carcinoma. So I used AI to corroborate this predictive value of cell-in-cell arrangement. What I did with colleagues was we developed our own deep learning algorithm to distinguish something that's cell-in-cell from a non-cell-in-cell arrangement. On the top, you can see cell-in-cell is where a cell is covered, is ingested by more than 50% of an external cell, and they have distinct cytoplasm membranes. On the right is a mimic, which is just 2 urothelial cells overlapping. We trained this on over 1,600 thin prep whole slide images. And at the end of the day, what we found was in those rare cases that have a cell-in-cell arrangement, it's usually only seen in high-grade cases. As you can see on the graph on the bottom, it's usually in high-grade or what humans call suspicious for high-grade cases. You do not really see a cell-in-cell arrangement in negative cases. And for those cases that were high grade and suspicious that had a biopsy or a cystectomy, I pulled those cases, and at least in half of those cases, I was able to find a corresponding tissue equivalent, as you can see in the image there, a cell-in-cell arrangement. So this hasn't really been published in the literature yet. Maybe one day I'll get around to doing that. But the point I wanted to make is that AI is very exciting, that I can now use AI to do my research and make discoveries and help us advance the field for patient care and give up the microscope to do so. So finally, I'd like to end off by saying, well, obviously AI is great and there's a lot of hype around AI. But how easy is it if we actually decide to use it in everyday clinical practice? So let's look at that. What I tell most of my colleagues, pathologists, cytologists, is not to panic that AI is going to replace them, but to rather think of AI as a tool that will augment and help them for their daily work. So if you're like this person who has to screw in those screws into the wood every day, and this could be screening pap tests, this could be looking at thyroid FNAs or whatever volume of cases you have to look at, if you had that screwdriver, it's going to be much easier to do that job every day. You will still be needed, but it will make your job easier. Now, there's a lot of hype around AI, as you are aware. This is what's known as the Gartner hype cycle, very typical of any new technology that's introduced into the field. And you can see that in the beginning, when technology is introduced, people's expectations are inflated, everyone's excited. And eventually, over time, when they start to realize, well, this isn't working as well as they thought it was, and it's got lots of problems, it's very expensive, and so on, people become disillusioned and eventually hit the top of disillusionment. What I like to do is encourage you is, should your lab be one of those labs working on this or testing or validating this or decide that you actually would like to use it, don't give up. Wait for the slope of enlightenment, which is eventually we will reach that plateau where it will be useful, just like it was with the automated pap test in many countries. We've reached a plateau where it is productive and helpful to use every day. Where would we insert these AI tools? That's also not clear. If you have a lab that's making slides and you scan your slides and a human then interprets them to generate a report, you could have the artificial intelligence algorithm run before the user even looks at the case. Some people call that a first read system. That could help you triage cases. It could help, if something's out of focus, do QA and have it rescanned, for example. If you need to order something up front, an HPV test, special stains, you could do all of that up front. It could even prepare the report for you, so it could speed things up. That's exactly what academic medical centers do, where they have registrars, residents, fellows, they prepare a report. The AI could do all of that, what I call a digital fellow. So it would prepare everything for you like a resident, registrar, fellow would, but at the end of the year, the trainee doesn't graduate, the AI only gets better year after year. Alternatively, you could have the AI run post-user. So if you're the user, you could say what AI you would like. If you find something, you could say, oh, okay, help me grade this case, help me count mitoses or whatever you need. So you direct the AI what to do. And then there's also AI that could run in the background. I am not aware of anyone building those kind of artificial intelligence algorithms. I wish they would, because as you know, if you are running a cytology lab, there's a lot of stuff you have to do, like cytology, histology correlation, and many other people would be interested too in doing sort of pathology, radiology correlation. And this could all be done in the background with artificial intelligence. One of the things that we're probably going to have to figure out how to do going forward is, if we have challenging areas, how are we going to solve them? Are we going to use AI to solve them? Or are we going to use molecular testing? I'll give you two examples. So the pap test. The pap test, as you know, for many years has been solved. We screen those looking at cytomorphology. AI now is assisting with that. So should we stick with cytomorphology with AI assistance to screen pap tests, or should we look at PCR for HPV? And many countries are adopting primary screening for using HPV testing for cervical cancer. But we do know that there are HPV negative cervical cancers, and some patients are being missed with just primary screening for HPV. I don't know the answer, but perhaps maybe a combination of AI with molecular testing may be the right way to go. Another example is the thyroid FNA. if we have thyroid nodules, and sometimes there are challenging nodules that we put into these indeterminate categories and hard to figure out where they actually belong. Many people have resorted to molecular testing. If you can afford it and it's available, some people are using, ThyroSeq Afirma testing. It's quite prevalent in the USA where people send stuff off for molecular testing. But what if you could get all the answers from the molecular features alone, especially with the help of AI? One of the things that AI is very helpful at doing is applying the AI at the bedside. So there are 1 or 2 companies now in the USA where you can do a thyroid FNA for a patient under ultrasound guidance, for example, and at the bedside, you put the aspirate into a little box, and that device right there and then will do an interpretation without even staining the material, and will tell you if it's adequate or not and lesional or not, with the help of certain sophisticated advanced imaging with artificial intelligence applied to that. And that can be done at the bedside without the need for a human to review that, and obviously avoiding all the expensive molecular testing. So that concludes my talk, and I thank you for your attention. And at this point, I am happy to go back to our organizers so I can answer any questions if you have any for me. Thank you for your attention.
Thank you so much, Dr. Pontanowitz. It so happens, for whatever reason, that there are no questions in the Q&A. So I think what we'll do is just proceed. And I have a couple of questions. The first one is, wow, a staggering amount of information. And really, this is frontier in so many different directions. My question is, you've pointed out obviously certain areas where inroads are being made, obviously in the cervix, urine cytology. But what about other areas that have higher stakes? For example, biliary tract cytology and pancreatic FNA. Although pancreas now, certainly in the States, we're seeing the core biopsies are becoming more prevalent there, but I think that biliary tract cytology is still obviously quite challenging. And so the first thing I thought about when I saw you mention about urine cytology and the cell-in-cell arrangement, I was immediately reminded of the work that the Mayo Group did, looking at morphological features and tying it to fish results, fish testing. So can you comment on sort of your thoughts about what's going on in AI and digital cytology, and what the state of play is in these higher stakes challenging areas?
Yeah, Leslie, that's a great question. So the first thing is that I do not think we will reach anytime soon a state where AI algorithms will replace us and everything we do on a daily basis. We have done those exercises where if you look at all the organs in the body, lung, breast, so on, and then all the diseases that can occur in those organs, carcinoma, melanoma, sarcoma, lymphoma, etc., neuroendocrine tumors and so forth, and then the type of preparations you can have for those, you would need at least, and we've figured this out, about 1,000 AI algorithms to do all of that work, which is on any given day, in any organ, with any preparation and any disease, you can make an interpretation. So I don't think we're going to make 1,000 AI algorithms for anyone's app store right away. So obviously the people that are commercially involved in this are obviously picking high volume, low hanging fruit for now. And those may not be the most challenging areas that we face in the cytology community every day to make diagnoses, which is some of the things you've raised. Bile duct brushing can be tricky sometimes, and the stakes are high, right? If a patient gets a Whipple procedure based just on a bile duct brushing, that's tough. Now, I am aware that people are working on these algorithms. In fact, I'm contributing cases to some of these, like the bile duct brushing. People are building large data sets. they are looking for real world cases. No one's used, like Dr. McHugh Alpine and others from South Africa suggested, well, if let's make synthetic slides and then, augment and speed up what we do. But not too many people are doing that yet. So the thing is, we're headed in the right direction. The target is high, which is many algorithms to be built. But the pace is pretty slow at this point in time. And so, as I pointed out, the only commercial algorithms really available for people around the world are the ones for pap tests now using AI. The others are all just research use only, and they, in someone's research lab, and they're not really available for all of us commercially. And I'm also not advocating that you go and build your own AI algorithm, plug it into your lab, and then use it, because who knows if it's safe. I recommend something a little more safe than that, which is we probably need algorithms that are well validated in many labs, and we need a recipe out there for all of us to follow. I will say that given this, and as the current president of the American Society of Cytopathology, and my concern is that that we don't really have a recipe what to do in cytology labs. I have assembled a task group for the ASC, and they are currently working on such a guideline for us, which will probably be published at the end of the year as a white paper, to give the cytology community some sort of guidance on what to do, if you would like to embark on this new area in cytopathology.
Fantastic. Thank you so much for that. And so actually, we do have a couple of questions that just dropped in. The first question is, what is your opinion on the utility of digital cytology in a low resource setting?
Yeah, so that's tricky. If you can't afford the technology, that obviously prohibits you from using the technology. But there are options that you can look into, such as, philanthropy, people who are willing to provide grants for research use. ASCP have been pretty good at providing help and resources in Africa. And so if you're in a lab in one of these African countries and you're listening to us today, reach out to the ASCP, reach out to your industry partners, or look at even federal options for funding. You may be able to bring in this technology and learn to use it, at least from a research point of view, validate it that way. And in time, I'm hoping that the cost of all of these things will come down. We know in the field of computer science in general, cost tends to come down, like data storage gets cheaper and cheaper. And I'm hoping that as things become easier to regulate and more people use these, that the cost of these systems will fall and the cost of data storage will fall, and that they're much more easy to use. Like you can put them on cellular networks. They don't need high fiber networks to carry the bandwidth of images and process stuff in the cloud, that it will become cheaper and easier. But I do acknowledge at this point in time, even for labs in the USA that have a lot of resources, it's expensive equipment, it's expensive to run AI in the cloud. And so, as I mentioned, it drives up the cost indeed, and we don't have good reimbursement. But the business use case is still questionable at this point in time.
And Dr. Pantanowicz, this is Dan. So one comment I would make specifically to the Hologic Genius system that you showed, which as Leslie's already stated, is a really brilliant, incredible system. In my conversations with Sarah and Philip and Allison and that group in trying to capacitate Africa in this regard, they aren't selling this device to anyone. It's just too expensive. They're placing them and thinking about subscription services. So even if we thought about placing an instrument, which wouldn't create a capital cost for an African site, what they need to be able to use that, as Dr. Lukandi has pointed out in his comment, is they need thin prep, right? They need that to be able to make the slides. They need to have that staining solution that you mentioned. And they likely need to have a Panther to do HPV screening in order to complement that because of the WHO requirements for that. So it's not, that piece of equipment is not the barrier. It's really the other infrastructure for needing to have a Panther, needing to have an HPV screening program, and have thin prep solution, the thin prep sampling available. That's really the barrier cost, because Hologic is, can help with the equipment, but they can't help with that supply chain. So a government really has to be committed. And I think small countries like Botswana, Lesotho, Swaziland, where they only, Guinea-Bissau, where you have 1 or 2 million people total, you could really create a cytology HPV testing, co-testing algorithm and justify it, and it would make sense. But you know, your Nigerias and your Ethiopias are going to have a challenge because the WHO is saying VIA, or HPV testing. So it's a lot more complicated. But I do think that the cost of AI, as you said, is coming down, and there are companies like Hologic and others that want to make it viable, but it's the other stuff you need in order to use it that also is the barrier. Just wanted to make that point.
Thanks very much, Dan. So there is another question here. Is there a scenario in which a certain number, parentheses 10, were screened through AI and compared to cytotext screening?
I think the question they're asking is when you compare a cytologist, cytotechnologist screening a slide to the AI, what is the comparison there on sensitivity, specificity? Maybe Dr. Pantanowicz or some other statistics from that.
Okay, so the statistics were favorable, usually in favor of Hologic, their system. I'm currently working with my statistician, and whoever asked the question, we will publish that soon. So the numbers are quite complicated. They're not as glorious as we thought they would be, but they're as good, if not slightly better than a human. So I will publish the statistics soon once I have finished confirming the final results.
Okay, great. So I think that we are now at the conclusion of the hour. And so I just wanted to wrap up by reminding our participants, we will have an echo session next month. April 19th, I believe, is the date on breast FNA. So please stay tuned for that. And many thanks to Dr. Pantanowicz for sharing his expertise. Clearly, this is a frontier in all of our fields, in pathology and cytopathology, and it will take time, but we have much to look forward to. So thank you again, and we will see the participants next time.
And just one more reminder, next month we have 2 sessions. We have the cytology echo on the 19th, and we have the Africa Calls pathology the following week. And I will be sending you all of those details as soon as we have the recording of Dr. Pantanowicz to share. That email will go out so you can register for the 19th and see the recording, and then you'll get details for the following week as well. Thanks so much.
Bye, everyone.
Bye.
Bye-bye.